Hi everyone, I'm Arjan Singh, a PhD student in the Photonics Inter-Research Group at the Cornell Center for Materials Research. This is the internet and how it's evolved since 1997. Each line on this graph is a connection between two host computers. And if you zoom into any part of this massive network, you'll see that every system that makes it function is the result of a long research effort focused on understanding materials. And now we're at the precipice of a new kind of network. Yeah, not that kind, but a quantum network that is meant to transport information encoded in a fragile but rich quantum state. But if we don't do the transfer right, we lose all the rich information provided by the quantumness of the state. One way to do it right is to use something called entanglement to teleport our quantum state. So we ask ourselves what new material properties we need to do this. But before that, maybe you're wondering what's a quantum state, what's entanglement, and what I mean by teleportation.
Beam me up, Mr. Spark.
A photon, a single packet of light, has a neat property called polarization. It can be vertical or horizontal. It can also be a mix, a superposition of the two. This is a quantum state. A and B are just numbers related to the probabilities of getting a vertical or horizontal polarization when we measure the photon. Similarly, an electron can be in a superposition of up and down spin states. A coin can come up heads or tails, but a quantum coin, which is not really real, can be in a superposition. And since we're talking about the internet, my cat is either awake or asleep, but his much cooler sister, Quantum Cat, can be in a superposition. For our purposes, this superposition is what makes a particle or object quantum. And when only two states are involved, we call these quantum objects qubits. What's neat about quantum states is that they can be entangled. I can entangle my quantum coin and quantum cat such that when I toss my coin and find it to be heads, I know without even checking that my cat is sleeping. If the coin turns up tails, my cat is awake. And this entanglement can occur for two quantum coins, photons, electrons, any two qubits. Further, this works at arbitrary distances, even when I put one of the qubits, say, on the moon. Now, I want to send my quantum cat up to the moon. And since my cat is a fragile quantum object, I'm going to use my entangled qubit pair to do it. Because the Earth and Moon qubits are already entangled, as soon as I also entangle my cat and the Earth qubit, a version of my cat instantly imprints itself onto the Moon qubit, effectively teleporting it.
Great Scott!
I know, right? But the Moon only has an imprint. For the Moon to get our original cat from the imprint, I need to measure my Earth cat and qubit and tell the Moon what I got, so the Moon can get the original cat back. This step makes the entire process not instantaneous per se, but hey, at least the quantum state is intact. And of course, you can't really teleport cats, only real quantum particles like photons. So, to create a globe-spanning quantum network, we need a way to efficiently create entangled qubits. Here's one way we're approaching this at the Cornell Center for Materials Research. A free electron, when trapped, can only have specific energies. We call this trapping structure a quantum well, which we could realize by putting electrons in a material sandwich. This is an image of 2 nanometer layers of gallium nitride in which electrons are trapped by layers of aluminium nitride. And since a nanometer is about 1,000,000 times smaller than the smallest ant, such a structure is grown one layer of atoms at a time in big, complicated tools. But when we put in the hard work, a quantum well can interact with light in useful ways. A photon of an appropriate energy will get absorbed, which you can measure. Even cooler, this structure can help you break a photon of large energy into 2 entangled photons of half the energy. You can also change the energy of photons, which is very important since you can embed your quantum state in a photon of any energy, and your choice might be different from mine. How efficient these processes are depends on how much something called optical nonlinearity our structure possesses, and all the material science and engineering we're doing is to therefore maximize this nonlinearity. Of course, before we can make a large quantum network, there are many more questions left to answer. Perhaps the one in your mind is why do this? Well, a more fundamental answer beyond just efficiency, speed, and security is that our world is governed by the rules of quantum mechanics, so a quantum approach to computation, communication, and simulation is naturally in line with it. And if nothing else, I hope we can at least use it to make better quantum cat memes. Thank you, everyone. That's my time. Happy to answer any questions.